Assalamualaikum warahmatullahi wabarakatuh. So we start with this chapter 10. So if we want to speed up the reaction or we want to speed up the association, so we can add the enzyme to the reaction, okay, or to the solvent. Okay, so here, here what we see is that the enzyme bind with high specificity to a substrate molecule, chemically modify it, and release the product, and then repeat the cycle. Okay, so the enzyme does not consume by the reaction, but it speed up the reaction. Okay, so without the enzyme, the same chemical reaction can still take place, but at a vastly slower rate. Okay, so here we can see that when we add enzyme, so we can speed up to 10 to the power 8 or to 10 to the power 12 mole per second. And nearly all enzymes are protein. Okay, so we have this protein in our body. Okay, so we can add this enzyme to speed up the reaction. Okay, so what are the reaction or the one of the known kinetic theory for this addition of enzyme? So we have this mechanism mentioned kinetics. Okay, so here these are we have the basic two-step model. So the first one, uh, the substrate or the protein or the reactant will add with the or react with the enzyme, making a substrate or a complex. Then from this complex, we produce the product. Okay, so then this E when uh, move from this produce the product, so E can go back and react with another substrate. Okay, so here Ks is dissociation constant, equilibrium constant, and K catalytic is the catalysis constant. Okay, so which one is uh, the speed of these two? Okay. Okay, so if we see that Ks is greater than Kcat, so here E E plus S becoming ES, then ES again becoming E plus S, does not or will not produce the P. Okay, so the concentration elevation is ES over E times S over 1K S. Okay, so if E total, the total enzyme in the solvent is the free enzyme and the attached enzyme or the substrate enzyme. So the concentration of the substrate ES can be written as ES equal to E total S over S plus K S. Okay, so we have the substrate. So the enzyme total will react with the substrate, and so it will again ES will increase until it saturates at or use all the enzyme, the total enzyme. Okay, so the product P, the production of P, this one, uh, V equal to the rate of production, V equal to K cat ES. So we can see again K cat ES. So K cat E total S over S plus KS. So we increase when S is low, and it will saturate when S is increased. Okay, so when S is low, it will be more reaction. Okay, when S is high or there is a lot of substrate, so only a total number of enzyme can react with the substrate, so it will be slow. Okay, so here you can see that when S low, okay, when S low, here K cat E total S and E S. Okay, KS. So we get this value. Okay, so this Ks is high. And first order as S high, the substrate, the concentration of substrate is high, so we can ignore this. This one cancel, we get V equal to K cat, the E total. Okay, so the speed of or the constant catalytic constant uh, will determine the rate production of the product. So and if no saturation, so if we have S high, so no saturation, so this one because the solubility of the substrate. Okay, so much of some of the substrate does not solute in that solvent. Okay, so K cat, the constant can be used as catalytic efficiency. Okay, so must be faster, but it will appear to be slower because of the time required for the dissociation. Okay, so here you can see that. Here we see here ES to dissociate, ES to dissociate to become P. If it's taking a lot of time, so K cat will be much slower. Okay, the rate of enhancement by the enzyme is equal to K cat over K naught. So this one is using the enzyme, and this one the uh, the rate where there is no enzyme or we do not use the enzyme. Okay, so we can see how the enzyme enhance the reaction. Okay, and the catalytic efficiency K cat over Ks. So which one is much faster? K cat production of P product or the reproduction of E and S. Okay, so here these are the so without the enzyme, the range is equal to 10 to the minus 17 to 10 minus 1 mole per second. Okay, so here you can see that uh, most of the enzyme or the enzyme we use the enzyme because the enzyme is very expensive, so we use a small number of enzyme. So if we increase the number concentration of enzyme, so the rate can increase. But to save the money, so we put the specific number of enzymes so that we can produce the product without uh, wasting the money. Okay, so here we have this steady state approximation. So here we can see that we have E plus S, ES, E plus P. So here we have the enzyme plus the product. K1 is the forward substrate binding and K minus 1 is the backward substrate binding rate. So solving this and the steady state dEs dt K1 ES minus K minus 1 ES minus K cat ES equal to 0. So ES, the concentration of ES equal to K1 E times S over K minus 1 plus K cat. Okay, so the total enzyme, so if we take the total enzyme is ET equal to E plus ES, the pre-enzyme plus the uh, the substrate enzyme or the complex enzyme. Okay, so the production or the rate of production P equal to K cat ET S over S K cat plus K minus 1 over KT. Okay, so we can find this K or this other Nicholas Menten uh, constant number. Okay, okay. So these are the we can get this value by playing with this S. So we can get or we plot the graph. So the half one is the Nicholas Menten value. Okay, so the more complex reaction, so we can have a lot of reaction using the enzyme. So enzyme uh, produce product number 1, product number 2, product number 3, or product to another reaction produce product number 4. Okay, so if in this case, so if we write DES1 and DES2 and solving this again using uh, metric notation, or for in this case solving this, so we're going to get the rate of production is equal to K1, K2, K3, ET S over K1 S, K2 plus K3 plus KT minus 1 plus K2. Okay, so the rate of production which depend on the S, but the rate depend on the rate of two step. Okay, so this one step and these are the first step and these are the second step. Okay, so we can get this value. Okay, and the pre-steady state. Okay, so we can see that it takes time for an enzyme to reach a steady state. So if we have E equal to E total minus ES, so DES equal to this equation. So here if S greater than the concentration of substrate is greater than the concentration of enzyme. Okay, so we can assume that S is a constant. So this one become a constant. C1 equal to constant. K1 S plus K minus 1 plus K cat ES. These are constant. So these are just first order differential equation. Okay, so solving it again, we are going to get this equation. Okay, using the our method. Okay, so when t is t approaching infinity, so we are going to get we'll go to the steady state. Es equal to et s s plus k cat plus k minus 1 k cat. Okay, and when s is greater than this Maclaurin factor k cat plus k minus 1 over k1, so we can ignore this as et times s over s, so we can slash s, so the concentration of the complex is equal to E total, meaning that this one meaning that all the enzyme making the uh, complex with the substrate. Okay, there are practical problems such as unknown fraction of the protein and variation in the fraction of active enzyme from batch to batch. Okay, so here even though we are saying that these are ES over ET, so all the enzyme can react or attach to the substrate, but so sometimes uh, we have a defect in our enzyme, so we are not going to get the same number again and again. Okay, so if ES can clearly measure in the pre-state domain, then a useful estimate of ET can be made. The enzyme. Okay, the how much enzyme that we can put or we should put on the substrate or in the solvent so that it can produce the product. Okay, and if we have the allosteric enzyme, okay, so here so many binding site. So here we can see that complex mechanisms still lead to the same simple qualitative dependence of substrate concentration. Enzymes have a single substrate binding site, so these are the enzyme with single site. But it's enzyme with multiple substrate binding site, so again with a cooperative behavior. Okay, so exhibit cooperative behavior and a sigmoidal dependence obviously on the S. Okay, the substrate. Okay, so here with writing back again the rate of production V equal to K cat ET equal to S to the power of N over S to the power of N plus K S. Okay, so these are the cooperative behavior. And these are the one of the model for this allosteric enzyme. So Monod-Wyman-Jaeger model. So we have this T and R state, T state, and R state enzyme. Okay, so this enzyme can meaning that it can be in two state, and there is a 4 binding site. So in the T state, so again go one by one, and this also one by one, but this T state can also become the R state of moving to R state. Okay, so we will have the concentration of the uh, product. Okay, not the concentration of product, but the concentration of the complex. Okay, so next is the where in our chemistry we know that when we put the enzyme or we add the enzyme, so if we hopefully we can lower the binding energy or the activation energy. Okay, so here binding energy is mentioned as reducing the height of the energy barrier. Okay, so we can reduce the energy barrier. Okay, and stronger contact between the enzyme and substrate can be harnessed for catalysis, and it's also possible to stronger contact between the substrate and enzyme to oppose motion in direction coordinate toward the top of the energy barrier. Okay, so we need that here by attaching the substrate to the enzyme, so it can make the if the let's say the substrate is the protein, so it will make it will fix the protein, and it will make easier for the ligand to attack the protein to produce the product. Okay, so here the alpha of k cat equal to exponential minus p a r t ln k s. Okay, so if we have the ks, the temperature and the energy binding energy, so we can see that the rate constant of catalysis depend on these three values. So we can increase the uh, catalytic uh, rate of rate of production. Okay, and as before in our chapter 7 and chapter 9, so we have the Kramer's rate theory. So binding energy aid catalysis. So we say that the binding make aid the catalysis, and the Kramer theory is for division over the energy barrier. J equal to dp pa exponential minus E dagger over kt square root of pi kt over P dagger. Okay, so we can change the variable, the diffusion constant, the activation energy, the probability of finding the complex at A point, the flux and the temperature. So we can speed up the reaction, or that one can the enzyme can speed up the reaction. Okay, so the first one is the proximity and transition entropy. Okay, so binding an enzyme to the substrate will restrict this motion. Okay, so kalau dia substrate saja dia laju, tapi kalau the binding dengan enzyme dia very slow. Okay, so it will restrict the motion. So substrate move freely in solution, able to do reaction, but this reaction will depend on the collision between the two molecules, second order reaction. Okay, so it will decrease, slow the motion, so making it easier for the ligand to attack the substrate. Okay, the enzyme assists this process by drawing the catalytic group and substrate together in the first order reaction. Okay, so here we can see that these are the potential energy of the intramolecular. So here Pa, so we have a Pa here, so it will do the probability and coming to this activation energy and become produce the product. Or here intermolecular. So when it come to this coordinate, so we do the lot of reaction and can produce from this side to this side. Okay, so move from this side to this side. Okay, so for the intermolecular case, psi is confined to a potential energy well on the reactant side. So the energy intensity of minimum psi equal to A U, the potential energy U psi equal to P A psi minus A squared. So the probability become P psi equal to exponential minus U psi over K T. Okay, so the rate for intramolecular K intra equal to this equation, and the rate for intermolecular uh, this reaction, this equation. So the ratio is K intra C inter. So we're going to get this equation. Okay, so when D intra equal to division of intramolecular equal to division in intermolecular, and E intra equal to E intermolecular. So the ratio become 1 over C pi PA over pi K. Okay, so we can get uh, this value. Okay, so we get the rate constant for intramolecular equal to this equation. So it will making the reaction by much faster. Next is the Rosenthal entropy. Okay, so if there is no enzyme, so the substrate can move freely, but with the enzyme binding with the enzyme, so by bring the reaction group into the correct orientation as well as the correct position. Okay, and the formation of complex involved in the loss of 3 transitional degree of freedom, the loss of 3 additional degree of freedom, and the gain of 6 transitional degree of freedom. Okay, so this restricted rotation should therefore give about the same enhancement of a factor of 10 to the power of 5 or 10 to the minus 7 uh, rate of reaction. Okay, so we can get 10 to the power of 10 and 10 to the power of 14 enhancement. Okay, so a much greater speed when we have this proximity and this restricted rotation. Okay, so A and B, protein and ligand near each other, and binding site of the protein is can easily be approached by the ligand. Okay, so it can be much faster. Okay, so here proximity and rotation uh, enhance the rate of reaction. Okay, and reducing the E dagger transition state community. In general, the rate of reaction characterized by enzyme have Q10 value of 1.5 to 2. Okay, so enzyme transition community can reduce E dagger by 2.8 to 5.6 kilocalorie per mole. Okay, so you can reduce the activation energy. Okay, and the enzyme can also interact with the substrate in its ground energy state to raise the energy and close the gap between the transition state. State. Okay, so meaning that it will also again decrease the activation energy from the reactant to the product. Okay, and when we add enzyme and substrate, so we increase the friction. Okay, so the environment of the enzyme altered and constant for division along the reaction coordinate, and then the rate will change. Very random motion generate friction, and such motion within a protein generate friction along the reaction pathway. And then the solution can contribute to this friction through the random motion of solvent and solute molecule. Okay, so the examples, the small protein pancreatic trypsin inhibitor, the flat aromatic ring in tyrosine rotate around the axis form the CC bond. So division uh, constant is equal to 2.3 times 10 to power of 11 per second. A modest shielding of solvent in fluctuation and a direction of friction to tyrosine within the protein. Okay, so this influence of friction on motion can be studied by varying the solvent viscosity. Only a low density, a low viscosity limit that applies to the gas. Okay, so here what we want to say is that uh, if the substrate is moving fast, but by adding the enzyme, so we can limit the speed of the substrate, so it will be easier for the ligand to find the substrate and produce the product. Okay, the last one. Okay, so for the summary of this chapter or this enzyme. So adding an enzyme can speed up the reaction, and the Kramer theory can be used to analyze and explain the reaction rate when we modify the temperature, the division constant, the solvent. So we can mean that we can choose the correct solvent, the correct size of enzyme, the correct size of the best size of the substrate to produce the higher gain of the product. Okay, thank you.